Hello, dear students. Today we are talking about receptor intracellular signaling. What's a receptor? In the beginning, we have to know what's a receptor. Receptor is a special molecular which is producing in our body. So it's a special molecule which is producing in our body. And uh, ligands. What's ligands? Ligands. It's mean substance that join to the receptor. For example, hormone, neurotransmitter, drugs, toxin, and even chemical substances, they are all ligands. So here it's a type of ligands. Hormones, neurotransmitter, drugs, chemical substance, toxin. All of them, they are binding to what? They are binding to receptor and producing biological action in our body. So receptor, again, the definition of receptor is a molecule to which the particular ligands bind, and the receptor is producing what? Producing biological action. When plasma protein, when plasma protein are binding by uh, hormone or neurotransmitter or drugs, they have no any effect in our body. That's you have to know just for your information. So so now I will explain for you. There is two different type of receptor. One type is on the surface of the cell, another type is inside the cells. So as I draw for you here the we have two type of receptor. One type of receptor is located on the surface of the cell. Another type is where it's inside the cell. So those type of receptor which they are locating on the surface of the cell, they are responsible for taking what? They are responsible for taking those ligands which they are large molecular weight, or in another way to say, which they are highly polar. For example, uh, insulin, growth hormone, FSH or TSH, they are large molecular and they cannot pass cell membrane. That's why they need special receptor for translation to for transfer to inside the cell. So there is another receptor which located inside the cell. So it's for those small molecular uh, substance, small molecular weight, which they are highly lipid soluble. So they are lipid soluble. They don't need any uh, receptor on the surface to transfer to the cell. That's why they can easily pass cell membrane and go inside the cell. Which substances like that? All substances which they are steroid hormone. For example, testosterone, estrogen, progesterone, vitamin D, glucocorticoid. They all have small molecular weight and they can easily pass cell membrane. That's why they don't need receptor on the surface. They need only receptor inside the cell for their activity. Uh, Example, those substances which they are uh, large molecular weight is growth hormone, FSH, TSH, insulin, peptide hormones, and those substances which they are highly polar. For example, catecholamine and acetylcholine. Catecholamine like epinephrine, norepinephrine, and dopamine. So, so in the short way, substance with large molecular weight, substance which they have large molecular weight or highly polar uh, receptor present on the surface, but those substances which they are low molecular weight, the receptor present inside the cell. Now I'm going to talk about receptor on the cell membrane. Those receptor on the cell membrane, on the surface of the cell membrane, are three parts. Uh, Superpentile receptor. This one is superpentile receptor. Superpentile is mean something like snake. So this look like snake. That's why we are calling superpentile receptor. Or in another way, we can call seven pass receptor. They have seven cross to seven part with the crossing surface of the cell membrane. Or in another way, G protein receptor. Why we call G protein? Because of G proteins, they can act inside the cell and produce biological action. Uh, it's one type. Another type of the receptor which located on the cell membrane is one pass receptor. Only one pass receptor. That's why we call one pass receptor. Or this one pass receptor, they have the enzyme which help to signal the cell. And another type of the receptor is cation channel receptor. So here it's special place for transferring cation. Uh, those substances which they are working on serpentine receptor or on 7-pass receptor. It's called catecholamine, prostaglandin, histamine, and acetylcholine and TSH. So example of catecholamine, it's epinephrine, norepinephrine, dopamine, prostaglandin, also histamine, and acetylcholine. Also they can work on serpentine receptor. So here ligands they can bind this receptor. They have effector dominant. Effector dominant, they can affect alpha, gamma, beta unit, especially alpha unit. When G protein is binding to alpha unit is separating from the gamma and beta, and it's starting producing biological action. So here, this energy we have here, it's called what? Called G protein. In the shortly we can say on the surface of the cell there is three type of receptor: serpentine receptor, one pass receptor, and ligand ion channel receptor. And here, how G protein work in on the intracellular function. How G protein here is working. So, for example, we have substance which epinephrine, and let's be work on what on the heart, like beta 1 adrenergic receptor. When ligand is bind to the receptor to bind to the receptor inside the cell is have effector dominant stimulating. This effector dominant is stimulating G protein. G protein is stimulating alpha unit, alpha subunit, and then alpha unit is become rich in the energy. Then alpha ring is separating from the gamma and beta, and then it will go and produce it will go and break down ATP. When it's breaking down ATP, start to have affection on CAMP. Then after that it will go back to uh, previous place. So whenever we put epinephrine on the cell, in the cell CAMP, it will go up. After breaking down ATP, CAMP, it will go up. CAMP stimulates enzyme. It's called name of it's called green protein. What's the name of this protein is prokinesis. Then this enzyme is attached to intracellular protein, and enzyme's protein becomes active and metabolizes changing. So CAMP is stimulating the protein here. This protein is called protein kinases. So protein kinases is producing special enzyme which the action on the altar of the cell, and then it's metabolized. So and after that genome expression is altered. In also a green protein may act on phosphorylation of the ion channel. Then the cell is starting moving in calcium cation. It will go out, and when cation it will go out, more Ca it will go outside. Then cell is become more electropositive. So here acetylcholine and epinephrine they have opposite effect. For example, they have opposite effect on what on 7 path receptor, or in another way to say, epinephrine and acetylcholine have opposite effect, have different effect on serpentine receptor. For example, in acetylcholine cholinergic receptor of muscarinic type, it's coupled with G inhibitory. So it will inhibit G inhibitory, it will inhibit G protein. That's why in this case CAMP decreased. But epinephrine on serpentine receptor, adrenergic receptor coupled with G stimulatory. So here in acetylcholine it's act as G inhibitory, but here as G stimulatory. So when we have G inhibitory, when acetylcholine act as G inhibitory CAMP, it will decrease inside the cell. But when it's acting as G stimulatory CAMP, go up. So enzyme which can break CAMP is what is phosphodiesterase, and when phosphodiesterase increase in our body, it means CAMP it will decrease. So only the enzyme which can break CAMP, it's called phosphodiesterase. It means if we have low level of phosphodiesterase in our body, we have high level of CAMP. If you have high level of phosphodiesterase, we have low level of CAMP, because they are breaking down CAMP. So for example, daily we are drinking tea, we are drinking coffee. This tea and coffee, they have they can inhibit phosphodiesterase, and when they inhibit phosphodiesterase, so amount of phosphodiesterase enzyme it will decrease in our body, so CAMP it will increase. So when CAMP it will increase activity of our brain, it will increase also. Also caffeine, it's working by the same uh, way. Caffeine also is working by the same way. That's why when you take a lot of tea or coffee, you get stimulated. Hearts become more active and brains become more active. So when microbe is producing toxin is taken by uh, respiratory epithelial, then alpha, gamma, and beta unit. Then toxins can bind to what? Can bind to alpha, gamma, beta unit and become non-function. Then it can't inhibit adenocyclase and the protein is off. So organism for cholera which act on GIT and multiply theirs which call it uh, vibro-GIT. Vibro-GIT. So the bacteria is called vibro-cholera. Sorry, it's this vibro-cholera. It's releasing toxin. The toxin is called cholera toxin. Then this cholera toxin it will go to the cell and destroy uh, alpha unit stimulatory. Then alpha stimulatory it can break GGP which binding by before which it was binding before. So so GTPs remain for a long time and alpha action on adenocyclase it will increase, CAMP is increase, GIT because the cell is producing a lot of sodium and other fluid and it's producing severe diarrhea. So when uh, organism for the cholera which act on GIT, when organism for cholera is acting on the GIT, they are multiplying there. That organism is called vibro-cholera and they can release special toxin. The toxin is called cholera toxin. So uh, when this cholera toxin it will go inside the cell and destroy alpha stimulatory. When they are destroying alpha stimulatory cannot break GTP which joined to them before. So if this alpha stimulatory there is GTP which they are always binding to alpha unit. Then when they cannot break GTP, it means GTPs remain for a long time with alpha unit and mean alpha action on adenocyclic is increased, then CAMP is increased, then the mucosal cell is producing a lot of Na and other fluid and it leads to diarrhea. Another way of effect of epinephrine on serpentine receptor when or we can say on 7-pass receptor when epinephrine is come and bind to alpha-1 adrenergic receptor which couple inside the cell GQ. Here we call this one is GQ and alpha and GQ is stimulating phospholipids. It's called phospholipids. And then phospholipase C is breaking phosphodylaenine phosphatase. Then they produce this is called phosphodylaenine phosphatase. This one is called phosphodylaenine phosphatase. When when alpha and Q they combine here, they are stimulating this one, and when they are stimulating phospholinkage C, they can take like Caesar, they can take phosphodidyl phosphatase, and then they produce DAC and IP3. DAC, it's uh, disylglyceride, and IP3 it's insodyl triphosphate, and activate IP3. Then after activation of IP3 on endoplasmic reticulum, when this IP3 is activated, it's working on, or in another way to say, it's stimulating reticulum. When reticulum is stimulated, it's destroy and um a lot of calcium is coming inside cytosol. Then this calcium they combine to uh, calmodine and stimulating the enzyme which called chemikinase, and it's lead to phosphorylation and metabolism which will alter. So how metabolism which will alter by this way? First of all, epinephrine is suppressing the serpentine receptor. Serpentine receptor have G protein, and G protein it's acted on alpha and Q. Then phospholipid is acting, it's working as a Caesar. Caesar will take phosphodiol no phosphate, and it's producing DAC and IP3. IP3 it's affecting on reticulum. When it's have affection on stimulation of reticulum, it's ruptured, and a lot of calcium will release inside the cytosol. Here now we will talk about different type of ligand which work on G protein and some clinical correlation. So different type of ligands we have, like which work different type of ligands which work on G protein coupled receptor. For example, cholinergic receptor, adrenergic receptor, dopaminergic receptor, cholinergic receptor, GABA receptor. This GABA receptor is very important, we have to know about that. For example, cholinergic receptor is divided by two parts: nicotinic receptor, which ion receptor, and muscarinic receptor, which serpentine receptor or 7 bypass receptor. Example of muscarinic receptor which act on serpentine receptor is antagonist to muscarinic receptor. The example of the drugs which they can work on muscarinic receptor, it's atropine, scopolamine, and pyrazipine. As we know, pyrazipine it's reducing the gastric acid secretion. There is adrenergic receptor. We have different type of adrenergic receptor. For example, alpha 1 adrenergic receptor, alpha 2 adrenergic receptor, beta 1, beta 2, beta 3 adrenergic receptor. Alpha 1 adrenergic receptor are coupled with G and Q system. So this is this one, as I told you in previous page, is acting IP3 and DAG. So IP3 it's producing a lot of calcium inside the cytosol and increasing the amount of the calcium. So drugs which can block this alpha 1 receptor, it's the drugs which can block alpha 1 receptor is phenethylamine and phenoxybuline. So they can work and block this alpha 1 receptor. And also prazosin and taurosin also, but they are selective alpha 1 adrenergic blocker. Now, alpha 2 adrenergic blocker are also coupled with the G inhibitory system. So when they are coupled with G inhibitory system, it means CAMP inside the cell, it will decrease, and potassium influx in the cell is happen. For example of the drugs which can block this receptor is yihimbine. The drug is called yihimbine, yihimbine or yihimbine, it's the same. So beta 1, beta 2, beta 3 adrenergic receptor, they are coupled with gastric with G stimulatory protein, so they can stimulate G protein, and they will increase CAMP, and activation of the cell is increased. The example of alpha 1 example of beta 1, beta 2, beta 3 adrenergic receptor, the drug example which they can block, which can block beta 1, beta 2, beta 3 is everyone know, like propranolol, metoprolol, acetaminophen, esmolol or atenolol or timolol as non-selective. So these two drugs, they are non-selective. Dopaminergic receptor is it have two part, D1 receptor and D2 receptor. D1 receptor is coupled with G stimulatory protein and lead to increase in CAMP. D2 receptor is coupled with G inhibitory and lead to reduction of CAMP. There is a purinergic receptor which have two types, A type and B type. A type is also have a serpentile receptor, and B type also have a serpentile receptor which is present on ATP. So another thing which I forgot for dopaminergic receptor, mostly they are acting on central nervous system. For example, in old age, when neurodegeneration is happen, and in substance like substantia nigra, for example, when neurodegeneration is happen in the brain. For example, if this one is, if it's brain, when neurodegeneration is happen here, when neurodegeneration is happen in the brain, for example, it's lead to loss of the neuron which supply the dopamine into neurotransmitter to the corpus striatum, and as a result person will suffer from Parkinson's disease. So in Parkinson's disease there is three main problem: tremor, akinesia, which mean difficulty of movement, and also rigidity. So GABA receptor, it's very important, you have to know about that. GABA receptor are receptor for gamma aminobutyric acid. It's neurotransmitter which releases through the central nervous system. So for example, if this neuron, there is GABA A receptor and GABA B receptor. GABA A receptor, it's release and binding with what, with chloride, and a lot of chloride, it will go inside the cell and cell become overloaded, become hyperpolarized. In GABA B receptor, also it's stimulating G inhibitor protein and lead to loss of potassium, and it will become extremely electronic negative and become hyperpolarizing. So the example of the drugs which they can stimulate GABA B receptor is baclofen and saclofen. The example of drug which can increase activity of GABA A receptor is benzodiazepine and barbiturate. There is another substance which also they can work on receptor, especially in another receptor in on they can work on serpentine receptor is TSH. As you know, TSH is released by interpituitary, so present in the thyroid follicular. For example, if this one is thyroid here, like this one is thyroid follicular. Here we have TSH receptor. Serpentine receptor is TSH is acting on what? TSH is acting on serpentine receptor. In some patients, this receptor is become mutant. For example, here we have receptor, it's become mutant, and it means the receptor is become abnormal. So after mutation, as you say, like mutation of the receptor, it's overstimulating follicular cells and undergo the excessive proliferation. So we can call thyroid adenoma. There's also LH receptor, which also they can work on serpentine receptor. LH is luteinized hormone. So this peptide, it's a special peptide. This peptide is working as against serpentine receptor. In some patients, it become dysfunctioning when this serpentine receptor is become dysfunction. When LH is become dysfunction on serpentine receptor, the person it will suffer from precocious puberty. What's precocious puberty? Precocious puberty, it's when early menstruation is occur. For example, you can see the child with 6 years old have menstrual cycle or menstruation. ACTH are also serpentine receptors. They can also act on serpentine receptors. They are present in on adrenal cortex, or in some families these receptors become mutant in the cortex and lead to familial glucocorticoid deficiency. There is another receptor, is called rhodopsin receptor. Abnormality of this receptor, it's lead to retinitis pigmentosa. So what's retinitis pigmentosa? It's a familial condition which genes of the rhodopsin receptor are affected. We have also some neuropeptide which they can work on serpentine receptor, which is a couple with the G protein. So neuropeptide is like vasopressin. Vasopressin is uh, sensitize like ADH, which sensitize in hypothalamus but release in posterior pituitary. So vasopressins, we have like V1 receptor and V2 receptor, which present on V1 receptor is present in vascular system, and V2 receptor is the last part of the neuron. So in the last part of the neuron we have V2 receptor. So if patient they have problem with ADH, or if patient cannot produce ADH, means patient lose a lot of water, and that condition is called cranial diabetic encephalopathy. AT2 angiotensin 2 receptor is present in where? It's in arterioles, in venous system, in zona glomerulosa also present. Also they can work on serpentine receptor. Opioids also. So opioids, vasoactive intestinal peptides also act on serpentine receptor. Oxytocin also act on serpentine receptor. It's produced, or oxytocin, as we know, it's produced by posterior pituitary. So we can say all these different uh, neuropeptides, all these different neuropeptides like vasopressin, like second angiotensin, like opioid, vasoactive intestinal peptide, oxytocin, all of them are released by central nervous system or in the circulation, and they are working on serpentine receptor. Thank you very much.